Thank you very much. My name is Jens Hammes. I'm not from university and I'm not from an institute, but I'm from the Carbon Drawdown Initiative, which is a philanthropic financed initiative from a family foundation. And you heard of column experiments, you heard about pyrolyze, but now we're coming to a greenhouse. So we decided after a few experiments in a field. So the Carbon Drawdown Initiative is working on this since 4 years. We decided to first build some, we call them XXL isometers. They're right here. They are rain buckets changed to a scientific object. So we have a more closed system to look at something. We're expecting to see an alkalinity signal or an increase in alkalinity by weathering of the rock. And after recognizing that we don't see any changes after 1 year and 2 years in our field experiment and in our XXL isometers, we decided to close the system even more and go to a more controlled environment in the greenhouse. So, what does the greenhouse give us back? So we can just say we have a controlled irrigation through the whole year of minimum 2,000 millimeters per year with collected rainwater. So we don't have any alkalinity background signal. We have nearly pure rainwater, which is usually the same. Of course, there are some heavy metals which change sometimes, but during the year we have the same water. Additionally to that, we can speed up our weathering with the constant temperature above 90 degrees Celsius. So in comparison to the field experiment, we're boosting our system by the factor of 2 to 3. If you're more interested in that, there's actually a blog post on our homepage, and you can find these blog posts with your QR code. What is another advantage? So, like you maybe have seen in our headline, that we have different soils and we have different rock materials. So, of course, different rock materials have different chemical potential, but the rocks are also, or the soils are also making a big difference. So we have soils in our greenhouse with different pH, C, organic content of different parts of Germany, and to put them all at one place, it also reduced costs and, of course, the logistics. So coming more closer to the experimental setup, these are our pots. So we have a bucket with soil and we have a bucket where we collect water. So it's just pretty easy. But we can measure gas in the headspace, the efflux which is gassing out of our pot. We have a PCO2 sensor right in to measure the CO2 concentration in the pore space. We can measure the soil, of course, and we can measure leachate. And leachate we are measuring in the greenhouse the pH, oxygen, conductivity, temperature, and the alkalinity by titration. And in the commercial lab, we can, of course, measure cations, anions, heavy metals, and so on. So, because people in enhanced rock weathering are quite often talking about alkalinity and cations and anions, I will today focus more on CO2. So our CO2 sensors are built, or let's say we built multiple prototypes, and now we've reached to, I think, prototype 5 or 6. And we compared it to a Lolium measurement device, which is known in the industry. And our system has the advantage that we can measure on one table 50 buckets at the same time. So we don't have to carry it around, or we don't have to buy 50 devices, which cost around about 30,000 euros. So that's actually making it more easily for us to measure the whole experiment at the same time, because you have seasonal and daily fluctuations of CO2. With this device and with the PCO2 sensor right here, we're creating 4 to 5, depending on the table which we're looking at, million data points per day to really have a significant CO2 signal and CO2 measurement. And this is then also measured not only on one bucket with one treatment, we have 4 to 7 replicas depending on our experiment. So to give you a rough fast overview, because of course 50 minutes is limited. You see the setup of our whole greenhouse right here. So we have different tables from 9, 0, 7, 6, 5, 4, and so on. And each of the tables had different soils. So we have the third soil, which is actually the soil from our field trial. We have Lufa soils, which are coming from an institute in Germany, which are handing out standardized soils for scientific projects. And we have some soils from farmers all over Germany. So in our greenhouse, we compare control buckets with just soil with different rock or also silicate materials, from glacial sediment to industrial sediments or industrial material, to calcite, which is actually used in agriculture, to mafic and ultramafic rocks. To show you how our soil is varying, we have soil with different pHs from 4.6 to 7.69. You might recognize that there are more colors than in the legend. It should just show you the range from the lowest pH, so 4.6 to 7.69, and with the next properties of soil, it will be the same. There are more colors. It should just give you a rough overview of what is in our greenhouse. Of course, the grain size distribution is also varying between fine silt to medium sand. The organic content of our soils are also changing because organic carbon could be interesting. So there are also people from Antwerpen here in the crowd who are looking at this. So the TOC of our soils is varying between 0.88 to 275, and we have one outlier where you might hear something in the next stage from somebody else about the Bramstedt soil. And we have different CEC, so cation exchange capacity, which is also important because if we have a rock material, the cations can stick longer in the soil or are more easily leached out. So we have a CEC from 2.9 to 26.3 meg per 100 grams of soil. So with this, I just want to show you how different the soils in our greenhouse experiment are. Because if we are just comparing one table right here up, the third soil with the different amendments, we have just run one result of maybe sometimes the alkalinity goes up or it even goes down with rock material. We actually don't know why this happens, because if we sometimes look at other tables, for example, the Lufa 2.1, which is really acidic, we have only 2 amendments where we have an increase in alkalinity, and we also have only 2 parts where we have an increase in conductivity. While if we compare this to the Lufa 6S, which is also around pH 7, and it has a background of carbonates in it from Marl, we see an increase in alkalinity in all of our pots compared to the control. Important to the control, because in the control itself it has also carbonates. So everything is mixed up. And if we try to model enhanced rock weathering later on, we could maybe just have an experiment with different amendments, but with the same soil. So one soil could give you maybe a really good example for your model, and one could give you a not so nice result. So because of this, we have the CO2 sensors, and we want to see if there's any changes. In general, the PCO2 concentration in pore space is mainly driven by biology and by the grain size distribution. So what you can see here is actually the start of an experiment right this year on the table 0, and you have the ppm on the side and the dates at the x-axis. So what I want to show you with this is just after building up the pots, mixing it with the material, we have a sudden decrease in the PCO2 with the alkaline materials, so the industrial materials like already mentioned, and we have an increase, of course, of the calcite, and a collection of PCO2 values of the control, mafic rock and ultramafic rock. So changes can be seen in PCO2 just at the beginning. To maybe show you that this is not only the case on the Luther 2.2 soil, but it is also changed last year. You can see the pH 7 soil here and compare just of the first month the PCO2 of the industrial material, which is very reactive, in comparison to the others. And of course, we want to compare this to the field trial, and we have the same pattern here with the steel slag with highly reactive material, which shows that something is visible in the PCO2. So coming from the PCO2, we now go to our CO2 efflux, which we were talking about before. So for everybody who's into chemistry units and so on, don't maybe get angry by seeing tons of CO2 per hectare per year for alkalinity. There is an explanation for this in the QR code if you're interested in that, but it makes it now easier to compare the 10 times of alkalinity with the same unit as the tons of CO2 per hectare per year as CO2 efflux. So what we see here is, again, third soil with different amendments. We have industrial material, we have mafic rock, ultramafic rock. And we see that we compare here to the amendment experiments to our control by the line of 0. If we have more efflux, it goes up here. If we have less, it goes to the minus. Of course, different amendments sometimes show a higher CO2 efflux or a higher alkalinity signal, but they are all at the same site, at the same pattern. If we now look at different soils with the same material, so with the same basalt, then we see that it looks totally different. We have less efflux, for example, for this farmer soil, and we have an increase in alkalinity. If we would now use this experiment for building up a model which predicts our CDR and at the same time our rock dissolution, it would be great. But if we just use this model on the soil where we have a degassing or an increased CO2 efflux, which could be produced by priming, so that microbial activity is just boosted, we would get totally different results also for the alkalinity. So it's really important, and that's actually my take-home message, that we could just combine our knowledge and our measurements of different soils with different rocks and build up a database which then provides us more insights in models and weathering. So feel free to scan the code for more information to our flux measurements and so on for our units, and thank you for your attention.